the other simple new concept you're going to have for this problem is that we have this delta HR, which is the heat of reaction for the chemical reaction in your system. And this has to do with simply a balance between what is present in the bonds at the beginning and at the end of a reaction, for instance. So this delta H R or delta HRXN really is, in a typical system where you're doing this, it is the sum of all of the different reactions taking place. But in your reactor problem, on the collaboratory, there's only one, so you don't have to worry about the one reaction. And the change here has to do with a change in the energy of the chemical compounds. There's a number of ways of thinking about this, but this is the energy net required or released by the conversion, in our instance, of A to B. And this can be treated as relative to how much reaction is taking place. So in the reactor system, you multiply this by the conversion, by the first order conversion of the Ca, which goes to Cb, of delta H Rxn. In this problem, we just specify what this is. And there's many ways of calculating this, from the types of bonds and the structure of the chemicals. And that's really useful for simple molecules, but in biology, you pretty much have to measure this. The large biomolecules become quite cumbersome to try to apply any of the simple things that are used for common small molecules and understanding what delta H reaction is. So measure this, get some baseline or estimate, and then use in your code. In your initial reactor examples in this problem, you have delta H reaction is equal to 0. But when it's not 0, like as we talked about before, it can feed back. Temperature increases reaction rate increases temperature in a feedback loop.